Welcome to the electronicshobbyblog.com. Today we're going to talk about capacitors in AC circuits. But before that, we're going to cover a little bit of AC theory. And we're going to talk specifically about the sine wave. Now, why do we talk about a sine wave when we talk about AC? Well, the most common form of AC voltage is the sine wave. It's what comes out of all of our household outlets. And the reason that it's a sine wave is because of how the electricity is generated. The electricity is generated by, well, you guessed it, a generator. And the way that generator works, and it doesn't matter whether it's a coal-fired plant or a gas-fired plant, nuclear, wind power, or if it's a dam, right? Something is turning a generator, and that generator rotates around a circle. So that's why we've got a circle on the board here so we can talk about the generator. And as that generator moves, there's an armature that includes wire windings around the armature that move through magnets. And as the winding moves into the magnet, it starts to generate electricity. And the more fully it moves into the magnetic field, then the more electricity it generates. And as it moves out of the magnetic field, it generates less. So let's look at how that works and why that means we get a sine wave. Well, let's assume, we'll use a phasor here to point, and let's assume we start here. And that's going to be the start of our waveform. And now, as the windings rotate, as the armature rotates, it reaches this position. And that happens an X time later. And we'll say that's right here. So we'll move there. Okay, then the armature rotates some more and we reach this position. And we're generating that much voltage. And then when we get here, we're generating that much voltage. And of course, when we get here, we've returned here. And this is the first half of the sine wave. And of course, as we move through the remainder of the positions, we generate the bottom half of the sine wave. And that's why AC voltage that comes out of your outlet looks like a sine wave. We range, as we range around the circle, from 0 all the way around to 2 pi. And that's radians. So 0 radians to 2 pi radians. So now that we know why electricity is most commonly in the form of a sine wave, let's talk about some of the parameters of that sine wave. So let's talk about some of the parameters associated with AC voltage, and specifically our sine wave. The sine wave itself, I've actually got 2 cycles of the sine wave written up here, but each cycle ranges from 0 to 2 pi radians. And so when we talk about the frequency, there's a couple of ways we'll talk about it. One way we're going to talk about it is in radians per second. And so it's 0 to 2 pi radians is equal to 1 cycle. Of course, this would be pi halfway through. Okay? We also measure the frequency in cycles per second. So we can measure it in radians per second or cycles per second. So for the outlet voltage, what's coming out of your wall is about 60 hertz. And so 60 hertz would be 60, in this case we're talking cycles per second, which is equal to the frequency in hertz, right? So the other word that we use, the term we use for cycles per second, is called hertz. So what comes out of your wall is 60 hertz. That means 60 sine waves like this in a second, which means that this is 1/60th of a second. Okay? It's also a certain number of radians per second. So if there's 60 of these in a second, right, 60 hertz, then how many radians are there in a second? Well, it's the frequency in hertz. So the radians per second, which we abbreviate using the Greek lowercase omega, is equal to the frequency, usually use a lowercase f, times 2 pi. So omega, to rewrite that, is really equal to 2 pi f. And that'll come in handy later when we talk about some other formulas. So let's clear the board and let's talk about some other parameters associated with the sine wave. So some other parameters associated with the sine wave include the voltage values, and there are a few voltage values, and of course power and current. And so the first thing we're going to talk about is peak voltage. And so the peak voltage is the voltage from 0 to the peak, and this is called V peak. Okay? We can also measure the voltage between the peaks. So from here to here would be V peak to peak, the peak-to-peak voltage. And so if this were plus 6 volts and this were minus 6 volts, V peak is equal to 6 volts, and V peak-to-peak is equal to 12 volts. Okay. Now there are other things we can talk about in the future. For instance, we can offset this sine wave by putting it on a DC voltage so that we can shift it up and down. So, it's possible for the sine wave to go up to plus 8, but only come down to minus 4. So this could be plus 8, and then this could be minus 4, and it's still, right, 12 volts peak to peak. But we've offset it, and so it's actually riding on a DC carrier in that case. So one other thing I want to talk about on sine waves before we go into capacitors. Let's do that. Okay, we're back. So let's take a look at our friendly sine wave again. And remember, we had a peak-to-peak voltage that we looked at, V peak to peak. And we said that this was 6 volts and minus 6 volts. So we have a V peak to peak of 12 volts. Another value that's very important, and a value that our meters measure, we'll get a value called RMS. And the RMS value, VRMS, is the root mean square. So the formula is that VRMS is equal to V peak times 0.707, which is 1 on the square root of 2. So VRMS is equal to 0.707 times V peak. So when you're measuring something on a voltmeter, digital voltmeter for instance, and you need to figure out what V peak is, and all you've got is VRMS, well, VRMS divided by 0.707 equals V peak. So let's take a look at how capacitors behave in AC circuits. So here's an AC circuit, 10 volts peak to peak, and we're going to say it's 60 hertz. So 60 cycles per second. We've got a 250 ohm resistor in series with a 10 microfarad capacitor. Now, in order to be able to use Kirchhoff's current and voltage law, which we learned about earlier, we need to be able to figure out what the effective resistance of the capacitor is. And actually, it's called impedance. And a capacitor's impedance, or reactance, X sub C, is a function of the frequency and the capacitance. And X sub C equals 1 on omega C, which is also equal to 1 on 2 pi F C. Remember, omega equals 2 pi F. So to calculate the reactance then, X sub C, which will be measured in ohms, we take 1 divided by 2 times pi times the frequency, 60 in hertz, times 10 microfarads in farads, so 0.00001 farad. And that comes out to be, I've already done the calculations, 265 ohms. So we're going to approximate it as 250, just to make the math easier. So let's go ahead and take a look at the waveforms in this circuit. You're going to see something very interesting. Okay, so let's talk about what's happening in this circuit in terms of the waveforms, the AC voltage itself. Well, very interesting. We know that the voltage across a capacitor can't change instantaneously. The voltage across a resistor can change instantaneously, but remember, capacitors charge and discharge, and they charge and discharge according to tau, if you recall our previous lesson. So it takes time for the capacitor to charge, and so it won't start charging to full value instantaneously. The resistor will. So the resistor's waveform, the AC waveform on the resistor, will follow the voltage source. So here's the voltage source, 10 volts peak to peak, 5 above and 5 below. And the voltage on the resistor will follow that exactly. So it will look like that. So remember, the voltage across the resistor can change instantaneously, but the voltage across the capacitor can't. The voltage across the capacitor is going to lag the voltage signal here. And so the voltage across the capacitor is going to be out of phase with the voltage across the resistor. And to do that, we look at a vector diagram. And the vector diagram, in this case, for a capacitor, so we have the vector for the resistor, which is 250 ohms. And then we have the vector for the capacitor, which is 250 ohms. And so what we're going to end up with is the resulting vector will be this. And in this case, since these are both equal, this is going to be 45 degrees. So in this case, the voltage across the capacitor is going to lag the voltage across the resistor by 45 degrees, which means that the voltage across the capacitor is going to end up starting 45 degrees late. So this is 180, this is 90, this is 45. So the voltage across the capacitor hold on. Is going to look like that. And the voltage across the resistor is going to follow so that at any time, so the current through the capacitor and the voltage across the capacitor are going to be out of phase, right? Because the current can change instantaneously, the voltage can't. And so those will be out of phase. And so the current through the capacitor is going to basically follow the current through the resistor because of Kirchhoff's current law. And what we'll end up with is that the power is going to be the sum of these. And so you'll notice that the power will be out of phase. And we end up with what's called peak power, which is the point where the power, the current times the voltage is the highest, and then we end up with average power. Now we'll take a look at it in the lab. Okay, so I've got a circuit set up on the bench. I've got a 10K resistor in series with a 0.1 microfarad capacitor. And I've got the signal generator set up to set out a 1 kilohertz waveform, 1 kilohertz sine wave at 6 volts peak to peak. First, I wanted to show you that although the voltage here is 6 volts peak to peak, when we measure it on an AC voltmeter, volts AC, it reads 2.12, right? And that's because what the voltmeter is measuring is the RMS voltage, which we talked about, VRMS. And so 6 volts peak to peak is 3 volts peak, and 3 volts peak times 0.707 is 2.12. So that's the RMS voltage. So now let's take a look at the voltage, how the voltage changes across the capacitor over frequency. Now let's go ahead and adjust the frequency, and I'm going to go from 1 kilohertz to 2 kilohertz to 3 kilohertz, and you notice it holds constant across the whole circuit. But let's look specifically now just across the capacitor and watch. You notice it's a little less than 6 volts, and as the frequency increases, remember the resistance or reactance of the capacitor is changing. Just the trigger here. And so the voltage, as I increase the frequency, right now we're at 6 kilohertz, 7 kilohertz, 8, 9, 10 kilohertz. And as I change that, you see that the voltage across the capacitor drops. So back to 1 kilohertz. And we'll look at the phase shift that we talked about. And in blue is just across the capacitor. So the last topic I want to cover for today is looking at how the reactance of the capacitor changes over various frequency ranges and what that means to us in circuit design. So I've put together a little scale here. It's log, and let's assume we've got a 1 microfarad capacitor in a circuit, and we want to measure the impedance or reactance of that capacitor at different frequencies. So we start out, I measured at 100 hertz, our capacitor's reactance is 1 on 2 pi frequency of 100 hertz, and then the capacitance, which is 0.000001 farads. And so that works out to be, it's a little over 15,000 ohms. So about 15K ohms. We'll approximate it to 15K ohms. So right about here on the curve. And that means that at 10 hertz, it would be at 150K. So about here. And at 1,000 hertz, 1 kilohertz, it's going to be at 1.5K. Because what we're doing is we're just changing the decimal here, so everything should change by a decimal. And at 10 kilohertz, it's at 150 ohms, and at 100 kilohertz, it's at 15 ohms, and so on and so forth. And what you'll find is that on a log scale, that's extremely linear. However, keep in mind, this is logarithmic. So if we looked at this on a linear scale, you would see that the reactance starts out very high and comes down very quickly. And the reason that's important is because if we put the capacitor in series with a resistor and we measure the voltage across the resistor, then at low frequencies, the capacitor reactance, the impedance, is much, much higher than the resistance. So that means that the vast majority of our voltage is going to drop across the capacitor. Remember our voltage divider circuit. But at high frequencies, the capacitance reactance, the reactance or impedance of the capacitor, is extremely low. And so at very high frequencies, the vast majority of the voltage will be across the resistor. And so what we've done is we've created what's called a high-pass filter. It will allow high frequencies to pass, but it'll block lower frequencies because at lower frequencies the capacitor has much higher reactance. We can add in another resistor and another capacitor here, and now this portion of the circuit works exactly the opposite. So now we have the opposite curve, so that at very low frequencies, the majority of the voltage will be across the capacitor if we're measuring here. And very little will be across the resistor. And then at very high frequencies, because the capacitive reactance is so high, then most of the voltage will be across the capacitor and very little across the resistor. And so when we put these two together, so this part of the circuit, remember, is a high-pass filter. This part of the circuit is a low-pass filter. It passes low frequencies and blocks high frequencies. And by setting the value of these components appropriately, we can actually create what's called a band-pass filter, which will pass only a band of frequency. So for instance, if we were designing an audio circuit and we didn't want anything lower than 30 hertz or anything higher than 16 kilohertz for example, we can create a bandpass filter that will only pass voltages or only pass signals that are in that frequency range. And we're going to talk about bandpass filters and low-pass filters and high-pass filters in subsequent episodes. So that's it for this episode. I hope you enjoyed that. Hope you learned a few things. If you did, please give me a like, share, and always appreciate a subscribe. And thoughtful, on-topic comments, of course, are always welcome. So thanks. See you next time. We're going to start active components and talk about diodes. Till then, cheers.